Hello and welcome to the 13th lecture of Machine Learning for Robotics and Computer Vision. In this lecture we want to talk about methods for going beyond convolutional neural networks. But before we dive into this topic, we want to talk about what happened in the last lecture. In the last lecture we talked about that always labeling large amount of data is very expensive and not something that we want to do always when we want to solve a novel task on a new data set. And for overcoming this we discussed two different methods to not label always a large amount of data, and this was the supervised pre-training, where we are using an existing data set to learn weights for our convolutional network and then only fine-tune the last layers. And by using this, we can then only use very few labeled images for learning a novel task. The other thing that we discussed in much more depth was the self-supervised pre-training, where we use a method like the SimClear or the momentum contrast or the build your own latent method to learn representations that are using non-labeled data. So we are just using different views of the same image to learn representations that help us then to solve the task that we want to solve. And by using the strategies, we can then use basically the data that we are generating for our target application, like medical images or something like satellite images, just without using any labels at all. And for all these tasks, we use now the so-called convolutional neural networks. And we hopefully now understand how they work and that they are very powerful, and the convolutions are the main building blocks there. And we use convolutions in there because they have some inductive bias, like that the spatial neighborhood of a pixel should also provide some information about the content of the image. And we could exploit the translational equivariance, which is basically that the convolutions, no matter where we apply it, will result in a feature that we can then use maybe to locate objects no matter where they are in the image. And both these inductive biases helps us to solve vision tasks in the end, and it's a very powerful idea that we can exploit in doing a lot of vision tasks like segmentation or object detection. And by using the idea of the receptive field, or by using deeper architectures, we can have very large receptive fields in the end. So as shown in this image, when we think of this convolution, then this works on these pixels, and when we are then getting these pixels then corresponds to basically then in earlier layers to large receptive fields that can then capture a lot of contextual information in these architectures. And by using this idea of this increasing receptive field with pooling operations in between, as we discussed this in the architecture lectures, we can then get very powerful feature representations over the whole image, and then also encode somehow this long-range dependencies between different pixels in the image. And the question now that maybe arises is that, are the convolutions the only way to solve vision tasks, or is it the only way to encode these long-range dependencies? And in natural language processing, in a very different field of machine learning, there came up a different way of capturing long-range dependencies. And since 2017, the so-called transformer methods are basically the method of choice for you solving natural language processing tasks. And the transformer architecture radically changed how natural language processing is performed. And very recently, this transformer were also applied to a range of vision tasks and showed there also state-of-the-art performance. And this is the thing that we will discuss more in detail. And the important thing is here that the transformer architecture doesn't use convolutions at all. But before we are diving into the vision transformers, we will look a little bit on how natural language processing was solved before 2017. And here, is an example which was first solved or successfully solved by using this transformer architecture was the so-called machine translation. And here the task is that we have an input sentence and embedding vectors of these words, and we want to produce an output sentence. Something like here, this translation from English to German. And the usual way how this was solved before using transformers was basically like using recurrent neural networks, but also convolutional neural networks. And the problem with this is that the recurrent neural networks, we are not discussing this now in more detail, but just to give you an idea, the idea is here that each token is basically encoded in the memory, and then the memory is used to encode the whole sentence, and then from this memory we want to then produce the output tokens. And the problem with this is that we have to encode a lot of the history of the sentence or the whole sequence basically in this very limited memory, and this makes it difficult to produce maybe longer sentences because the long-range dependencies, maybe the last word is depending on the first word, are very hard to encode in this memory in the end. And this is showed very limitations for longer sequences, so especially when you're thinking of that you want to produce maybe a whole page of text where maybe the last sentence has also some coherence to the first sentence. And for this, the transformer architecture was very promising because for the translation task, the transformer architecture looks something like this. So we have now here an encoder and a decoder, and as you can see here, the encoder gets all tokens at the same time. So the sequence the transformer block sees is basically the whole sequence, and the vectors that we are using here are always d-dimensional, and the transformer blocks takes these d-dimensional vectors, does then some operations with this, and then produces d-dimensional vectors as output. Each layer produces this. And then just to give you a short idea, I will not go into the details how this works, so you can look in the Attention is All You Need paper, how then the translation is really done in the end. But the idea is that the transformer blocks produce some output representation that can then be used by the decoder. And in the decoder we have basically the already translated part. Then we have transformer blocks that are depending on the information from the encoder, and that produces then the output probabilities over the words that are produced. So we are producing one word at a time, and then this word is then fed back into the decoder, and then the next word is produced. And the advantage is that the transformer block always has full information about the whole sequence, and then can use this information to produce the next word. And by using this, we can then also have the long-range dependencies that we are interested in. So now to look at how the transformer block is actually implemented. The transformer block has basically two parts. So here you can see that we have some normalization layers in between. Here in this case layer norm, it's very similar to the batch normalization. And this ensures that we can also have very deep architectures without vanishing the gradients or exploding gradients. And we have in the first part self-attention block, age times of the self-attentions, and then we have in the second part multi-layer perceptron, fully connected layer with a non-linearity in between, and this is then giving us the output. And as we had in the ResNet architecture, we have also the skip connections that help us also to train deeper architectures here. But we now look first at the so-called self-attention block. How does it work? So we have here represented our input sequence. So we have n tokens, and these are d-dimensional. So we have in this case 3 tokens of dimension 4. And these are first fed through a linear layer, so that we are producing now transformed sequence tokens for the query, the key, and the value. So these are the learnable parameters of the self-attention layer. So we have linear weights for the query, for the key, and the value. And this query and key are now used to produce weightings that we can then use for the values to combine them into new vectors, so to basically transform them into new vectors. And for the this combination of the queries and the keys, we are now computing the basically the dot product between each query and each key. And this gives us then an n by n dimensional matrix of attention weights, where each entry corresponds basically to the scalar product between the key and the query and the key. So we are basically computing the similarity between each query and each key. And this gives us then this n by n dimensional matrix. And this is then scaled by the square root over the dimension, so to make it that it stays in a certain range in the end. And when we computed basically the similarity between this so-called query and key vectors, we are then using a softmax operation, in this case a row-wise softmax, so that the sum over each row sums up to 1. And then we are combining this with the value, so we are computing this attention matrix, which is basically then a row-wise sum, which each row sums up to 1. And we are then producing the matrix product between this and the value, and this gives us then a weighted sum of the values that we have here. And this is then the output that we are producing, and this is then the so-called scaled dot product attention. And in the when you look in the attention is all you need paper, then this is formalized like this. And this operations that we are using here gives us now a way to encode somehow the certain attention patterns. So where to look basically in the values and how to combine them into new representations. And since each of these attention blocks has now a specific way of looking at our input and combining this into a new output, we want to have basically multiple parts of this. So therefore, as we had in the transformer block, we have many of this, so multiple heads that are producing this recombined inputs. And for this we are then having the so-called multi-head attention. And the idea is here very simple in the end. We are not having only one self-attention layer, but multiple of them. And we are producing again query keys and values, but now reduce it to dimension divided by the number of heads that we have. In this case, this would be maybe 3 heads, and then we are producing outputs. And these layers are the layers as we discussed before. They are computing the attention weights between the query and the keys, and then weighting the values with this, and then producing outputs x1, x2, x3, and then to combine them again such that we are getting then, that the output is again the same size as the input. We are just concatenating these vectors together and then produce have a again a linear activation linear layer, linear combination that is giving us and then the desired output. And this is then the so-called multi-head attention head. And this is then this part that produces our outputs, and then these are fed into a multi-layer perceptron. And the multi-layer perceptron is just a fully connected layer that now works on each individual token or embedding vector of the input. So therefore we have here the x times w1, and w1 is weight matrix that projects our d-dimensional vectors to dff dimensional vectors. In the case of the NLP transformer, this is a 2048 dimensional vector. And then we have our bias. And as you can see here, we have a ReLU activation, that is our nonlinearity in this case. And then we have a second layer that just projects the DFF dimensional vector back to the d-dimensional vectors that we want to have, and then produce our output again. So this is then the MLP layer that we have. And around that we have our skip connections that help again to train the deeper architectures. And this is basically then our transformer block. As you have maybe noticed, currently the order of the inputs doesn't matter for the self-attention block. So it will produce just the attention weights as before, and doesn't care about the order. And this is not maybe something that we want to have when we have machine translation or translation in general, because the order of the words in a sentence is of course important. And for this, to solve this, the authors of the Attention is All You Need paper use the so-called positional encoding, which is just a constant that is added to the inputs. So each input token is added this positional encoding, and we have here for the even dimensions, we have a sinusoid function that gives us a value, and for the uneven dimensions we have basically a cosine. And how does this work? It's just a simple example here. Here we have our sinoids and cosines for different dimensions. And when we now want to encode, for instance, the token at the position 28, we are just looking at this slice of the functions. Then we have our embedding vector for the word at the 28th position. And then we are just looking up the values of the sinus and cosinus at the specific position. And then we are getting maybe these values here, like for the fourth dimension, this is the blue curve. So we are looking here at position 28, and this gives us minus 0.98. And then we can do this also for the fifth dimension, the sixth and seventh dimension, and this gives us some vector. And you can think of it like a smooth binary vector in the end. So instead of having just values between only 0 and 1, we have now values between 0 and 1. And when we are now encode a different token at position 71, then we are getting maybe these values out. And by using this positional encoding, the transformer can basically know where the different tokens are localized in the sentence and use this information. And the positional encoding will also play later a role for the vision transformers. When we now look at results that were achieved at the time, we see that the vision transformer got very good results on the translation from English to German, but also from English to French. And these were very promising, especially when you compare it in terms of the training costs that were used for producing these results. So this very promising results led to much research in natural language processing, and the larger transformer models had a wide range of capabilities for different natural language processing tasks. So basically when you now want to tackle maybe a natural language processing task, then you definitely have to look into transformers and use transformers maybe also. And the more interesting part was that you could use very large corpora of text and pre-train the transformers and then transfer the models that you learn to very different tasks with only maybe very few training examples. And then the models got bigger and bigger. So we have here the XLNet, and you heard maybe also of the GPT-3, which is a very large transformer model. And this very large models could achieve very interesting capabilities, like in the GPT-3 then generate coherent text for a specific input and then give you a completion of the text that was very convincing in the end. And the question is now, can we maybe directly use the transformer models also for images? And when we look at the complexity of the self-attention, then we have to note that we have this n by n dimensional matrix here. So, and this is the crucial part. When we just now represent an image with every pixel as an input token, basically, then this would result, for instance, for the normal ImageNet resolution to over 50,000 tokens. And when we have this 50,000 tokens, we have to produce basically a 50,000 by 50,000 dimensional matrix. So we soon will reach the limitations of the memory. So the question is now, can we still use the transformers for images? And is there maybe a different way to do it? And a very simple idea to apply transformers to vision tasks was basically then the so-called vision transformer. And the idea was here, to basically use, as before, the standard transformer encoder with the multi-head attention and the MLPs, as we discussed before, and apply this to vision tasks. In this specific case, image classification on ImageNet. And the very promising result was in the end that the vision transformer could achieve also state-of-the-art results. And now we will look more in depth into how this was achieved. So to get rid of this problem with the self-attention that we have to produce an n-dimensional matrix, we are not using pixels, but we're using patches. So we are splitting the image into patches of size 16 by 16. So each patch has a size of 16 by 16. And this gives us then only a limited number of embedding vectors that we want to have for our self-attention. And the patches are then just reshaped into a vector, so that we have now patches, the patches reshaped into a vector of 3 by 16 by 16, because the dimension for this we don't care so much about, so the dimension is then something like 768. And we are then using a linear projection to project this to the embedding vector that we want to have in the end for the transformer. And for this dimension, the authors of the paper used just a reprojection to the same size, but also larger sizes of the embedding vectors that they are then using for the transformer layers. When we then come to the positional encoding, as we had it for the words, we also want to have this positional encoding for the patches to know where the patches are located in the image. And for this, the simple idea was to just count the patches with one-dimensional index up, so from upper left to the lower right, and this then produces our linear indexes of the patch. And then we are using the positional encoding as before by adding the sinoid or cosine function on top of the embedding vector that we are producing. And this gives us then the input for the transformer. And the transformer encoder is then, just as before, the self-attention with the multi-layer perceptrons, and then we have multiple layers of this, and then we are attaching, so this is a specific case now here for the vision transformer. They are also having an input token which corresponds to the class token, and the idea is here that the class token should then capture all the information from the other passes in the transformer. And the idea is here that we attach to the output of the class token a multi-layer perceptron that produces then our classes. And because when we are using backpropagation, this will naturally lead to the behavior that we are capturing basically all information that we need to this specific output. Because the loss and the backpropagation will basically lead to the behavior that we can aggregate via the self-attention layers in between this information layer. So, and the MLP in the end maps just the feature that we are getting out from the transformer encoders back to the classes that we are interested in. And when we then look at the results that the vision transformer achieved, then we can see that the results for ImageNet, but also for other transfer learning tasks were reaching state-of-the-art or even surpassing state-of-the-art. So therefore it was widely recognized that there's something happening there, that the transformers can be used also for this specific task. But one has to note that this was only possible because Google had this very large GTF dataset with 300 million images, which can be then used to pre-train the transformer and then use this on this downstream task. So that means the transformer was not trained basically on the ImageNet dataset itself, but it was trained on this much larger 300 million weakly labeled dataset for pre-training. Still, in this case, the vision transformer huge, which then uses also patch size 14, used 32 transformer layers and had overall over 600 million parameters. But as you can see, it provides very compelling results. And one interesting thing that turned out to be in the paper then, that when you look at the distance between the patches that were attended to, so by using the attention weights in the different heads, then you can see something interesting. So on the x-axis you see the network layer and the depth, basically the encoder, the layer, the depth of the encoder layer, and what you can see here is basically the distance between the patches. So that means the higher this dot is, basically the larger is the distance between the patches that were used in attention weights. And as you can see, already in the earlier layers there are heads that also attend to very far away patches basically. And therefore the property that emerges here is basically that the transformer has already the capability to basically also use long-range dependencies already in earlier layers. And in convolutional neural networks, as you remember, we can only achieve this by having very deep layers where the receptive field of the convolution is then taking care of this long-range dependencies. And this is a very cool result in the end, that you can see already that there's something different happening than in the normal convolutional layers, or what would possibly happen in convolutions in the end. So we have already this large long-range dependencies already in the earlier layers. And this is something that is very different from what happens in convolutions in the end. And but the problem with this is now that we have this very powerful method, but we need very large data set to pre-train it. So, and then the first thing, of course, to look at was how to actually get rid of this pre-training on a very large data set. And for this is then one other paper investigated how to achieve basically similar results with much less or with just using ImageNet for pre-training. And the insight here was that because the transformer has less inductive bias, we have also to do more data augmentation in the end by using now more data augmentation. So these are the parts here in green, and using more regularization, that is the part in yellow, we can get very good performance also with just using ImageNet as pre-training data set. And here this table, you can also see it maybe in the slides then more detailed, is then showing what is basically needed to achieve this, and when you then leave out certain parts, how does this affect the performance. But the insight here is that because the transformer has basically less inductive bias, it needs either to see more, so larger data set with very different images, or it has to use, or we can basically exploit data augmentation to give the transformer basically more to see or to learn from. And this idea of investigating how to efficiently train transformers were now recently also investigated again by a group of researchers from Google, and then the question was how to train actually the vision transformer in an efficient way. And here the authors looked specifically on the part of the data augmentation and regularization, and how this is traded off via using maybe larger training data size, or how does this relate to using more compute in the end. And in the study, so luckily they did it, it's like 50,000 experiments strong, and there went a lot of compute into this. So, but the insights from this, so the key takeaways, I just shortly want to summarize here. So when we look at the data augmentation and the regularization, so this so-called Aug Reg, and compare this to the size of the data set, then we see basically that by using a small data set and then using the augmentation, so on the x-axis you always see here the data set, and then what happens when you also use the strong data augmentation and regularization, then we can see that by using a smaller data set with the augmentation, we can basically get similar performance as with a larger data set. And this, of course, then is very promising, because we can maybe use here the larger ImageNet data set, the so-called ImageNet 21K. This is this 13 million image strong data set, and apply there our data augmentation and get a similar performance as using this very, very large data set, which is not publicly available from Google. So, and so that means with the right amount of regularization and image augmentation, we get similar gains as increasing the data set size. And when we now look at how to use these models, then we can see that the transformers basically need more data in the end. So when we now train here, these blue curves are different transformer models that are trained without any pre-training on the specific data set. Here on the left side you see a data set with just 3,000 images. Then you can see that no matter how long you train, you will never reach the performance that you get when you're just using a pre-trained network. So the green curves are basically vision transformers that are already pre-trained on a larger data set, and then they applied on this specific data set. So in this case, this image data set with only 3,000 images. And as you can see, with not so much compute, in the end we are already getting very good performance. So we are getting networks that already achieve nearly 100% accuracy here. When we then go over to larger data sets, then we can see that we can basically use more compute to reach basically similar performance when we are training from scratch. But in the end, it turns out that we can get similar performance by just using a pre-trained transformer. And so therefore also the title of the slide, transfer is the better option. So if you're in a compute restricted environment, which usually normal people are, then it's maybe better to just use a pre-trained transformer in the end. So, and the warning that is basically coming out from this, for small data sets, training from scratch will not result in the models that get a good accuracy in the end. When we now look at the transferability of the transformer models, then one trend is clear. Here on the x-axis you see different kinds of models, so different sizes of models, so from a very small model to very large models of image transformers. Then you can see that here for pre-training the models, basically the size of the data set is very important. So the different curves correspond to different ImageNet regimes basically. So we have in the yellow curve, that's the normal ImageNet with 1.2 million images trained for 300 epochs or pre-trained for 300 epochs. Then in green you see the much larger ImageNet 21K dataset, which is then here in this case the green curve is pre-trained with 30 epochs, and then the blue curve is pre-trained with much longer training scheme with 300 epochs. But as you can see, especially here on this natural data sets, you can see that there's a large gap between this very small pre-training regime to the large pre-training regime. And so pre-training on more data yields in the end more transferable models, so in the end. And maybe one explanation for this is that the transformer needs to see more variations to get basically the inductive bias that are maybe already present in the CNN. But when we now look at these results, which are basically achieved on the supervised pre-training, then the natural extension, when you think back of the last lecture, is then of course maybe we can just exploit self-supervision. And this was of course then also explored for the vision transformers. And here this paper proposed to use a very similar architecture to the MOCO, where we have now here this student network. So this is a vision transformer, so they are basically the same architecture. But the thing is now that the teacher is producing some probability distribution over a certain number of classes. But these classes are not now predefined in a way that they are certain real classes in the end, but they are just achieved by the centering in the end. So, and what is now used for the pre-training is that the student network tries to reproduce the class distribution that is produced by the teacher network. Even though the class distribution itself maybe has nothing to do with a certain class, in the end it just tries to produce the same probability distribution in the end. And like in the MOCO approach, the teacher is just updated by using a momentum update of the student weights, and by using this strategy one can get very good results, as shown here on this slide. So the authors also applied this to ResNet 50 and showed that you get also by using this strategy very good results in the end. But you can of course also apply this to the transformer architectures, and as you can see you can also reach very good performance with this vision task. So but why this paper was also producing some excitement basically in the vision community was also because when you then look at the class tokens and then visualize the attentions for the class tokens in the image, then you can see that there are somehow object segmentations are emerging from this attention weights. So that see there were no specific classes given in the beginning, but when you now take certain parts of the distribution that is coming out and then look at the attention weight, then you see that there are some objects basically emerging from this. So it's just using self-supervision in this case. And this is maybe a promising prospect of what is maybe somehow happening inside the transformer that maybe can be exploited for other tasks, maybe even object segmentation in the end. So we now looked at image classification and the self-supervision for image classification, but of course the prospect of the transformers or the success of transformers for the image classification also now inspired, of course, also people to use it for other tasks. And the tasks that we are now looking at are again tasks that we also looked in the lecture more deeply, the object detection, but also the image segmentation. And for object detection, the so-called DETA approach was proposed, which basically uses CNN features in the beginning, but uses then an encoder-decoder architecture, just normal transformer layers again. So we have the transformer encoder and the decoder, and the specific part that was now here used was that we can basically query the transformer decoder for outputting a specific number of object bounding boxes. And the idea is here that the decoder produces exactly the number of desired object bounding boxes in the end. So that means we don't need to have non-maximum suppression in the end to figure out where are the objects located. And to achieve this, the network used basically this class and bounding box prediction in the end with fully connected or multi-layer perceptrons on top of the outputs of the decoder. But it can also produce so-called no object part. And the thing that was used for training was basically to have the decoder parts to match to the ground truth labels via using the Hungarian method, and then using this to then output the desired bounding boxes in the end. And this is a very cool idea in the end, to just have basically just as output the bounding boxes that you are looking for. So nothing extra, nothing less, you are just getting the bounding boxes that that represent some objects in the end. And by using this idea, you can then see that the results also confirm that it's getting much better results in the end in terms of average position, and the prospect of this is maybe then more explored in future. We now looked at the detection part. We can also have a look at the segmentation. So also there was, of course, the transformer applied, and as before, the transformer layers in the end, or the transformer blocks, are just the standard transformer blocks from the natural language processing. Nothing changed there. In this case, the idea from the vision transformer was used so that the image is first split up into patches. Then linear projection produces with the positional encoding the input for the transformer, and then the transformer produces for each patch basically a patch feature. And then comes the decoder part that produces then the pixel-wise class distribution that we are interested in. And for the class distribution, the pixel-wise class distribution, the authors now propose two different ways, which are pretty standard when you remember this from the segmentation lecture. So the idea is here to just reshape the embedding vectors again into patch features, so to say, and then use just convolutions to upsample this. So we have convolutions and then bilinear interpolations to get then the larger feature map size in the end. And then using this, we get then the probability distribution for each pixel. So this was then the so-called progressive upsampling, or like it's called in the result table that we will have a look at, it's the PUP. And then they also propose to use maybe some idea like in the feature pyramid networks, that you use the feature representation that are also coming out into intermediate layers of the transformer architecture. And for this they are just again reshaping the features into the image representation again, so that we have basically patch features, and then they are combining them similar to the feature pyramid networks, and then upsample them to the desired image size that we are interested in to get then the pixel-wise class distribution in the end. And again, when we compare this to the state of the art, then we see that the SETR approach, here are different variants of the upsampling. Here you can see the progressive upsampling, but also the multi-layer aggregation, and you can see that this reaches something like 50% MIOU, which is significant improvement over the state of the art, but just using these ResNet structures. But when we then also look at the cityscapes dataset, then we see also there a decent improvement over state of the art convolutional networks. And here this is maybe a specific part, because they are using here also some attention parts in there, but still have some mainly convolutional parts there. And this SETR approach provides strong results on ADK 20K and the cityscapes dataset. But since now the transformers are around, people also investigated, is every part of the transformer maybe essential to achieve these results? And the first thing that people looked at was, is the self-attention even needed? And concurrently, different groups investigated this idea, also in a very similar fashion. And here I'm just concentrating on the MLP Mixer. And here the idea was to take the features, which are patch-wise features, and just transpose this. And then use on top of this the multi-layer perceptron, and then to reshape it again into original size. And then comes the fully connected network, or the MLP. This is basically the same part as before, but this part is then just somehow mixing the features together from different patches. And by just using this idea, we have then this mixer layer, which is just replacing the self-attention now with this transposed MLPs. And then we have again the same structure as before, so we are dividing our image into patches, and then use linear projection to get the embedding vectors that we then need for our mixer layers. And instead of the class token, they are now using here global average pooling over the outputs of the mixer layers in the end, and then some fully connected layer to get the class again. And in this case, the MLP has now not a ReLU inside, but a GeLU, which was also, I think, used in the vision transformer. But this is just a small detail. So when we now look at the results again, then we see that this so-called mixer architecture is here with this purple dot gets very similar results to the vision transformers, but also to the other convolutional neural networks on different data sets. So here we have ImageNet, real ImageNet, then the VTape dataset, which is a dataset of 19 different tasks for transfer learning. And you can see that the mixer network is sometimes getting a little better results than even the vision transformer, but at least for ImageNet it's a little bit worse. But still, some interesting thing that we are coming now back again to multi-layer perceptrons, where I said in the beginning maybe that's not the best idea. So, but as you can see, the research is progressing, and at least this idea of separating the image into patches is somehow also used in this case here. So therefore, you see the development. So when we now have an outlook, this whole area of transformers and how to use transformers is of course a highly active research area. So you basically can, every week look at arXiv and see new papers popping up, investigating new ideas. For instance, combining CNNs also with transformers is of course the natural thing. Maybe we can combine here in this paper from Xiao et al. Is like combining CNNs in the early layers with transformer in the later layers, and then getting very promising results also from the training stability. That is now maybe the next thing that happens. So maybe use at certain locations a little bit of the insights that we already got for the CNNs to make also the transformer architectures better in the end. Also saw papers that investigated to just use CNN architectures to distill basically the knowledge into the transformer architecture. So maybe using very well pre-trained CNN architecture to then maybe drive the training progress of the transformer in the end, but also by using the initial weights, basically some weights from a CNN and so on. So the combination of the old and the new is basically something that is heavily investigated here. Some other directions for transformer research is of course using deeper transformer architectures. So maybe going a little bit back to the beginning of CNNs, where we had problems with training deep architectures, which were then overcome with the skip connections and using something like this. And this is investigated, but also reducing the cost of the self-attention. So there are certain ideas coming up how to get rid of this n-by-n dimensional part, maybe even with the just replacing this with MLPs in the end, but also using some hierarchical structures. So because currently in the architectures that we discussed now, basically the input dimensions or the number of tokens basically stays always the same, but there also works in the pyramidal vision transformers, for instance, investigate how to get some hierarchical structure very similar to the structure that we have in CNNs, and of course then also having maybe better decoders that are maybe also getting rid of convolutions in the end, like in the SegFormer paper, where we have also, there are some developments. So, but as I said, every week someone else is coming with new ideas and showing that we can go further than the current state of the art with this model in the end. So, and with this I'm already coming to an end. So in this lecture we discussed the success of the natural language processing or the transformers in natural language processing motivated also the investigation for vision tasks. So we discussed in particular the image classification, but also the detection and segmentation. And yeah, since the transformers have somehow less inductive bias, the hope is that it can maybe exploit more information from the images that maybe cannot be represented by just using a convolutional neural network. And of course, everything is basically driven by the promising results that we are already getting by the transformer architectures. So, and maybe also some properties that are maybe appearing, like this object segmentation mask that from the self-training comes. But yes, certain things that maybe can be exploited in future. So currently it's maybe in the phase of that again, years of research in CNNs are now leading to architectures that are easily trainable, very well transferable and so on, and maybe this progress has also to happen in the transformer, and maybe different ways of doing this in the for the transformers. And maybe this is also leading to maybe a paradigm shift, so maybe a combination of CNNs and transformers in the end. So like I discussed maybe in this little outlook, but yeah, it's very uncertain. So maybe next year I'm already telling something different, so maybe forget about transformers, they are not working or something like else. I don't know, but I don't believe so. So they are very, signs that the transformers will stay in the end. And with this, hopefully could give you outlook on what is currently happening and what is maybe in future happening in the vision research, and also related to this, vision is also an important part of robotics, and therefore this is also the last lecture. So therefore I'm ending this lecture not with saying see you next week, but see you next year maybe. Then thank you for your attention, and goodbye.